Many people who watch this video are already familiar with the subjects of rational numbers, real numbers, and so on, but never thought about what the rational number or irrational number are in its most fundamental sense. In our previous videos, we already covered the canonical representation of rational numbers. In fact, rational numbers can be represented in its canonical form as the set of A, B, or as I call it, P, Q, where P is the integer and Q is the the natural positive number, and the greatest common divisor between them is 1. So they are irreducible. Feel free to watch my previous episode and follow from there if you're not familiar with this. But in this video, I'm just going to rely on this well-known fact. So what is the purpose of this video? In this video, I would like to construct the number which is irrational. That's by definition, it doesn't belong to the set of rational numbers. And one of the such examples is geometrical. If we have a square with both sides equals to 1, we already know from the basic school, from the primary school, that its diagonal equals to, by Pythagorean theorem, square root of 1 square plus 1 square, which is the square root of 2. Such numbers that are possible in real life, right? It is possible, kind of. We do have some sort of square root of 2, and we study these numbers in a school, but we don't know what kind of number it is. It is a real number. It is not the rational number. In fact, the rational numbers, they have some sort of gaps, but we're going to cover this a little bit later. So this square root of 2 is the number which doesn't belong to rational numbers, it belongs to real numbers. But how to show that? How to show exactly that this is not a rational number? We can state this. How to show that? How to prove mathematically that this number is not rational? So the goal of this video is to prove that square root of 2 and similar representations, similar numbers, they are not the rational number. It doesn't belong to the set of rational numbers. One of the most common proofs here is just using the canonical definition of rational numbers. Essentially, we're saying that we're using the reductio ad absurdum, which is the proof by contradiction. We're stating that by reductio ad absurdum, we're stating that there is such representation P over Q, or there are such numbers P over Q, right? P, which belongs to integer, and Q, which belongs to natural numbers, such that greatest common divisor of these two numbers equals 1, right? Because we assumed that square root of 2 belongs to the set of rational numbers, such that square root of 2 equals to P over Q. This is by definition of our set. It follows from here. So what does it give us? It gives us that if we square both sides of this equation, we got 2, right? Which is the equivalent to saying that P square equals 2Q square, which means that 2 divides P square. And then by definition of an even number, P square can be represented as 2R, where R belongs to set of integers, which means that 2R square equals to 2P square. Therefore, for R square equals 2P square, oops, sorry, this is Q actually, this is Q square, which is equivalent to saying that Q square equals 2R square. That means that 2 divides Q square as well, and therefore these two numbers are both even, right? Which means that this is not R, let's say this is R prime squared. Doesn't matter. That means that greatest common divisor of these two numbers is not 1. It can be 1 because it is like 2R1 and 2R2, for example, and that's definitely not 1. This is at least 2. Therefore, greatest common divisor is not 1, and, well, this is already contradiction. This is already the contradiction. That means that our initial assumption was wrong, and 2 is not in the set of rational numbers. So that's one of the simplest and one of the most obvious proofs to demonstrate that there are certain numbers which are kind of possible in the mathematical reality, but at the same time, they are not rational numbers by definition of what rational number is. And that leads us to the conclusion that there are certain gaps in the set of rational numbers, and we have to establish these gaps, and we have to show that this set is incomplete, and there are different sets which are complete. For example, the real numbers, a set of real numbers, and I'm going to get to this point in our next episodes.